as an operator and just general operational considerations. So that is what we'll be spending the next 2 hours reviewing. I'd like to stop every maybe 20 minutes and see if there's any questions, discussion, and then we'll just keep going. So know that although we're here for 2 hours, there will be moments that you get to break and breathe a little bit. With that being said, I'll jump to the first thing. So what are PFCs? PFCs, also known as perfluoroalkyl substances or PFAS, they were used and they are still being used in stain, oil, dirt-resistant materials, firefighting foams. You know, anything that has some stain or water resistance is what's kind of using it. We've probably heard of like Teflon and things like that. It has wonderful properties for being resilient and not breaking down. And that's the exact reason why now it's an issue to treat. They last, they stay for a long time. You may have heard of them as forever chemicals because of this, I guess, wonderful quality to not break down too easily, which makes them great for a consumer product, not so great later on in the environment. They are made up of a carbon chain with fluorine atoms, some oxygen. And the reason they're of a concern right now is they don't break down very easily and they tend to accumulate in the blood. It has been found everywhere in the world, including the Arctic and Antarctic. It's just pervasive, it's everywhere. And the reason it's a concern now is it's been linked to having effects in growth, development, reproduction, some cancers of, you know, non-Hodgkin's lymphoma. They're still in the early stages of studying it, but it has been linked to some hormonal and immuno issues. So in 2016, the EPA came up with some lifetime health advisories for 2 of these compounds. Taking a step back, the PFAS compounds, there's about 5,000, potentially more compounds that fall under this group of chemicals. The 2 that we're most concerned with right now because of the current regulations are PFOA and PFOS. Back in 2016, the EPA came up with a lifetime health advisory of 70 parts per trillion for combined concentration of PFOA and PFOS. Again, those are just 2 of the 5,000 or thousands of other compounds in this family. It was non-enforceable, non-regulatory, but it started to create health awareness and concern. In California, in August of 2019, WEHA came up with recommended notification levels and response levels. So notification is just that, hey, if your water source has above these 6.5 ppt for PFAS or 5.1 ppt for PFOA, you need to notify your customers that it's present. Response level of 10 ppt for PFOA and 40 ppt for PFAS, then you had to do something about it. So in January of 2020, California says any water system with an RL above an RL, they either take it out of use or treat the water delivered or send a notification to their customers of, hey, we're sending this to you at these levels. So that's kind of how we got here and why we're here now. It's also why in California, there's, especially down in our area, you're seeing a lot of run to get treatment. It was a very short timeline for people to react. Now, the rest of the country, because there's no federal standard, it is not enforceable. This is just a California standard at this point. However, the process for federal regulation has begun. I don't have a timeline of when that will be done, but California is definitely one of the first to respond to this level. Where are they found? Like I said earlier, it's globally spread. It's everywhere. In the US, this map shows kind of the hot spots. And probably no surprise to anybody here, it's where a lot of the population lives, but it really circles around airports, military bases, and then industrial sites that produce or use PFCs. In airports and military training areas, the main source is firefighting foams. It's still the most effective method to put out jet fuel and rocket fuel and all those very risky fires. So that's why you're seeing it around military bases. And then the rest is, like we said, these stain resistant, oil resistant products that are just everywhere in our products and consumer things. So in 2016, a Harvard study found that 194 out of almost 5,000 water supplies were PFCs were present. That it serves 16.5 million people, and from this map you can see like the areas impacted are very population dense. So 66 of those 194 were found to have PFOA above the advisory limit. That's the combined 70 parts per trillion. If you remember a couple years ago, they did a study to have like all the drinking water wells tested. A lot of that data is coming from that study. And drinking water from 13 states accounts for 75% of the detection. So it is a little bit localized. And in Southern California, we're definitely feeling it. So the next part of my presentation will be talking about the types of vessels that are used. Probably a little bit out of order for this presentation, but traditionally what we're seeing in this area is using either carbon or ion exchange as a treatment solution. So I'm going to talk about the types of vessels that are out there for use with carbon, ion exchange media, and potentially some novel sorbents depending on what those are. So I'm going to jump into a little bit about the different types of vessels out there and the advantages of each and challenges of each. So going back a little bit, most of us have seen these large vessels. They tend to be 10 or 12-foot diameter vessels. With PFAS, the larger vessels are a little bit more popular, and I'll get into why that is. But this is what they look like. The footprint is rough for like a system, which is 2 vessels, and the piping is roughly 14 feet by say 25 feet, somewhere in that range for a single system. And a system, when I talk about it, is the 2 vessels with the interconnecting piping tree and piping. So as this picture depicts. So when you're considering a vessel, you want to look at the under drain design. There's several different under drain designs, and I'm going to touch on 3 of them. The things you want to consider are the flow distribution. Are you getting complete usage of all your media? Are you minimizing pressure drop? In other words, are your pumping costs going to be impacted by what you choose? How easy is it to perform a media change out service? How easy is it to maintain the vessel? Are you going to be in there replacing parts all the time, or can you plug it in and not worry about it for years and years? Also, speaking of maintenance, what about the vessel lining and other parts that may need repair and maintenance over the years? And lastly, vessel height. Sometimes these are in residential areas. You may want to consider the height of the vessel and how that might impact the residents nearby or building regulations. So the 3 building under drain designs I'm going to focus on today are the hub and lateral, the internal cone, and the external ring header. The picture I showed a couple slides back is the external ring header. That is the one that Evoqua predominantly offers, but we can provide the others as well. And each system kind of has its pluses and minuses. All right, so first we'll dive into the hub and lateral system. The advantages of this system, let me go back to just what it is first. So this is just that. There is usually like a center line and then a bunch of radials, or in this case, kind of like an H pattern, or where the water goes through this this hub and lateral system with a bunch of nozzles to treat the treated water. So this is at the bottom of the vessel. The media sits atop it. The influent untreated water comes in the top, goes down the bottom, and then the clean water goes through these nozzles, then through this network of pipes and out the effluent. What's nice about this system is it does have good flow distribution because there's lots of nozzles, tends to have a low pressure drop, and because it sits within the bottom of the vessel, just kind of gets bolted. You can see the crossbars there where it's attached. You can line the entire interior in a single coat. There's no additional seams, and then this unit sits there. So it's good from a point of internal coating being one consistent piece. Disadvantages: large number of nozzles. If you're going to do maintenance and have to replace a broken nozzle, which sometimes happens, you'll have to evacuate the media, you'll have to do confined space entry, and it could be a little bit more maintenance. Also, too, it's a little bit more challenging to do a media change out because you have to work around those laterals. Not terrible, but just something to consider. I do not oftentimes see this design in the size systems that most municipalities are using these days. You know, larger flows, I don't see this too much. The next two are what I most commonly see in most municipal drinking water systems. The next design is an internal cone style underdrain. This is, from the outside, it looks like a large cylinder. They tend to be a bit taller because inside they've accommodated for this cone. And the cone has many nozzles. I think in like a 12-foot system, there's somewhere around 120, 130 of these little nozzles. The advantage of this design is good flow distribution. Got a lot of nozzles, a lot of flow. You know, you're really getting your media used. Pressure drop, it says low pressure drop. I've sometimes seen customers have issues, it depends, but pressure drop could be a concern. And because of the cone bottom, changing out the media is super simple. Gravity's our friend, it pours it towards the middle. So a great advantage of this one is the media removal. The disadvantages of this one are, again, there's a lot of pieces here, right? You've got 100-something nozzles. So if one of those, it's greater chance of something breaking. And to make a repair, you have to do confined space entry. The other thing too is with this design, there's the outside shell and then there's this internal cone. So you have to do confined space entry under the cone to change out the nozzles. I've had some customers where you have to clean out that under kind of like dead space on occasion. So maintenance could be a little bit challenging with this design. But overall great flow distribution. Backwash pressure due to the nozzles is a maximum of 20 psig. And with the coating, you have to coat that under section below the cone and above. So there's a couple more seams and with just some extra considerations. There's also weld seams along the interior of the vessel where the cone is affixed, and that could pose corrosion issues or over time. The last design is the external under drain or external ring design. This one is, there's a ring with 8 large screens that pop up through the bottom, and they've got these, they're much larger. So you saw the little nozzles before, those are little, you know, maybe 2 to 3 inch diameter. These are, you know, about 8-inch diameter stainless steel screens. Now there's only 8, but they're much larger. What's nice about this is you get good flow distribution. There's a lower pressure drop because there's bigger nozzles instead of a bunch of small ones. It does allow for one seamless internal coating. So similar to the hub and lateral, you just have your large shell, the whole thing gets coated, and then these screens get affixed. Also too, if you have to do maintenance, you just drop the ring header. So you could actually do maintenance if you need to on the vessel without confined space entry. That's a nice advantage. One disadvantage is not always optimal for spent media removal. The bottom is a little bit flat, so sometimes you have to use a pressure hose and kind of wash down the edges to get everything, the last little bit of spent media out. But not too big of a deal. Just compared to the cone where gravity's your friend, this one takes, could be a little bit longer to get the last little bits of resin out of there, or carbon. I'm gonna pause here. Do we have any questions, Stephanie?
Yes, actually we do. As it relates to best practices in the removal of PFAS, is there any media type or manufacturer that has proven to be more effective than another?
So, such the diplomatic answer. It depends on your water quality. So I'm going to get into a couple of different options, but depending on your water quality and what the background stuff is, sometimes carbon's better, sometimes ion exchange is better. And then as far as say the question again, did it relate to vessels or more media?
As it relates to best practices in the removal of the PFAS.
So it depends on what's in your water. If you have different levels of TOC, one might be better than the other. It really depends. Down in Southern California, I am finding that carbon and ion exchange are doing both very well. Ion exchange right now is tending to show better results at also removing short chains. But carbon is doing both, and I'll get into that a little bit further about the advantages and disadvantages of both, but okay. I don't know that I can answer it that much more without going into the second part of this presentation.
Okay, another question is, any issues with clogging of the nozzles with, for example, calcium buildup?
I have not seen that. We do have a couple sites that every couple years we do, after a carbon change out, we'll go in and we'll do a cleaning of all the nozzles. It's not usually calcium buildup, it's more like fines have kind of built up over the years. Sometimes we'll replace broken nozzles. This is in the cone design. I've not had to do this with the external ring header, but I do not see an issue with calcium buildup. Usually if there's calcium or scaling in the water, like you have scaling potential, you'll see it crystallize at the top of the bed, and you'll get a scale layer at the top of the bed that creates kind of like a crust. I'm not often seeing things down at the nozzles.
Okay, one more question. Where does the cost lie in pros and cons of the different systems?
Okay, so hub and lateral, I think, is the least expensive. Cone bottom versus septa, they seem to be pretty similarly priced in the market. So equipment wise, very similar. It kind of comes down to preference of design, and then maybe some height restrictions, right? The cone bottom is another 4 to 5 feet taller than the underring design, so sometimes that presents a challenge.
Okay, that's all the questions we have that I see right now.
Okay, then we'll keep going. The next thing I'm showing here is, depending on whether you're using ion exchange resin or carbon, you may need a distribution header at the top of your vessel. Resin, when it's flooded, gets very fluid, right? It's very light and fluffy, and it likes to move. So you have to do an inlet distributor. Now this is at the top of the vessel, so the water's coming in the top. This inlet distributor kind of diffuses it and causes it to spray, so that it's not just pounding down on the resin and potentially moving it out to the walls. If you picture if it was just shooting down from the middle of the vessel, it would kind of cause all the media to expand out and create kind of like a canyon in the middle. And then you would get short circuiting, you wouldn't get the best use out of your resin. Now with carbon is a little bit more stable. You don't need quite an elaborate inlet distributor. You can do more of a single point with a hat that kind of does still cause the spray, but you're not so worried as with resin. Resin it moves quite a bit once submerged. The reason to kind of touch on this is you want the top of your media to always be as flat as possible. You don't want it to tilt to one side. You don't want it to kind of blow out towards the walls. You also don't want it to cause a cone kind of in the middle. And the reason is, if it's not flat, water is going to find the path of least resistance. So it's going to go to the shortest part of your bed, and it's going to ignore all that other media. Once you're operational, your media becomes your most expensive part of your operation, right? So you want to use every bit of it that you can. And getting proper distribution and keeping that bed as flat as possible is key. One of the questions that came up was calcium, right? So if you've got anything in your water that might foul your media, you want to take care of it ahead of time so that you don't get that crust layer, anything that could be impeding the flow and your bed. So that's inlet distributors. Next thing on a vessel, we'll have sample ports. These are used to track where the contaminant is in your bed and how your usage is going. So we talked about if the bed's uneven, it's going to go towards, the shortest part of the bed, path of least resistance. Sample ports that are, at the top, middle, and bottom 25% of the bed, or we call this the 75% port, the one that's the lowest, help you track how the contaminant is moving through the bed. And it's a great tool to figure out, oh my gosh, there's something going wrong inside, right? Because once these are loaded and turned on, you're really not opening up the manways to check on them. So this is a way to monitor what's going on. Each system, there's usually 3 or 4 along the side. And then there's another one at the effluent. At the bottom of this drawing, you can see almost near the cement, there's the effluent. Or in this case, if the left vessel is your lead and the right is your lag, that would be the midpoint between the two. And then on the opposite side, it's kind of hard to see, there's a little blue cap there. That would be your system effluent coming out of the lag. So this is used to do your sampling, to meet your permit, and then also to help you track how is your media performing. What does an ion exchange system look like? So their ion exchange and carbon systems are very similar. Some of the differences, we talked about that inlet distributor and ion exchange needs one that can spread out and slow down the flow a little bit more. Also needs smaller mesh size screens at the bottom, so that ring header, so it can accommodate the smaller beads. It also needs pre-filtration. So down here in this little schematic, you see these 2 little pre-filters. We recommend a minimum of 5 micron pre-filtration, a minimum of 10. 5 is best practice. And with ion exchange resin, you really want to prevent any type of fouling. So the scaling, the silt, anything from that could possibly coat the sides and prevent, ion exchange from happening. So definitely in an ion exchange, I often get asked, should I do this pre-filtration in my carbon system? You don't need to. It does increase pressure drop across the system. But if you know you have a lot of silt or some other sand coming up from your well, it's maybe not a bad idea. And if you are having pressure drop issues, maybe go up to the 10 micron for carbon. But carbon, I don't always see these pre-filters unless you know you have an issue. Another question I get with pre-filters is, how often do I need to change them? Varies greatly depending, again, how dirty your water is. They're usually changed out when the differential pressure increases 10 to 15 psi over a clean filter. Or it could be limited by even less than that depending on your pumping capabilities. Sometimes people have to put a booster after this treatment system to accommodate their distribution requirements. So that's what a system looks like, ion exchange. Carbon's very similar, just take those away. This is a data sheet, a lot of information on here. This is, Evoqua has what's called a CIX dual use system. So we've created a system here that is interchangeable for carbon and resin. We're finding with the PFAS market, giving people that flexibility to switch between resin or carbon has been helpful. So here's some information. I oftentimes get asked, you know, how heavy are these? It's about 200,000 pounds when operational. The footprint of the system is roughly 14 feet by 25. Like if you're building a pad, that's what you need. Now, how did we determine what we were going to use and what is the best technology? It's kind of starting to now address the question I got earlier. We can do pilot testing or RSSCT. Pilot testing is actually out in the field where you are treating a, oh my gosh, I'm blanking on words, a slipstream from your well. So your well is actively pumping, you're slipstreaming a couple GPM, and we're running it through these little 3-inch columns, and it mimics your real life situation. Sometimes we increase it to double speed so you get results a little bit faster, but a pilot scale so far has proved to be a very accurate way to compare different technologies in real time using your water. We match, when we design the skids, we match them to the hydraulic loading rates you're expecting, and then we'll adjust the bed depth to get, you know, results faster to speed it up a little bit. These ones do take a lot more time and labor because they're running at most 2 times speed. And these products stay in service for about a year. So even double speed, you're only going to get results about as soon as 6 months. You know, so it's not a quick test. It takes a lot of analytical, and it can be labor intensive and a bit expensive, but it is accurate. In the example here, there were multiple columns and we were testing different ion exchange. And then in the far right, those were some novel sorbents. You can't see into this picture, but there was an adjacent skid with slightly larger columns for carbon. And we were testing a variety of carbons to see how they all compare treating the same water. Got some great data. This, to give credit where credit is due, this is a pilot over at OCWD. They did a very extensive testing, I think 8 or 10 different carbons, as well as 6, I think, ion exchanges, novel sorbents, and now they're doing a phase 2 with even additional medias. Oh, here's their pilot. They call it phase 1. Here you can see they also had pre-filters, the 5 micron to mimic real life conditions. So that's that. Rapid small scale column tests, are known as RSSCT, is a bench scale lab test that's also used. This one you get results within like a week. It is very high speed. It's most commonly used with carbon, and they're starting to develop more methods for resin. And what this is commonly used for is to predict adsorption, you know, if you're comparing 2 different medias to see which one lasted longer. It's not as good as predicting, hey, this will last 200 days in the field versus this one lasting 210, but it will tell you, hey, product E lasted longer than product C. So it's a good tool to show, A, you're getting removal, 2, this product works better than this one, and you get results quickly. Cost for something like this is, I want to say it's somewhere around like $8,000 to $10,000 to compare 2 different products, and then each product you add on would increase that cost, mainly due to sampling and analytical costs. So great tool if you do need a quick response, maybe for permitting or something like that. But if you're trying to get and estimate true bed life, the pilot might give you more accurate results. Oops. Sorry, my computer voice freezing. Okay. Going into the PFAS removal solutions. So more technology is coming out every day, but the three most common solutions we have in front of us right now for removing PFAS from drinking water are membranes such as RO or ultrafiltration, ion exchange resins, or granular activated carbon. Carbon is named best available technology by the EPA right now for organic. So if you've had any like chlorinated solvents or PC, TC, TCP, any of that in your water, and you are already treating, great. You're also already treating PFAS. So that's, it's great because it kills two birds with one stone. You can also reactivate the spent carbon. So disposal becomes a bit easier. You can also landfill, but carbon has that nice feature that you can send it to reactivation, burn off the contaminants, and either reuse it if it's done as NSF react and return, or it just goes for an industrial use. Here I have a little bullet point I probably should edit. It says reactivation removes liability. That is a big question mark right now. There's a lot of study going on. Is PFAS completely destroyed during reactivation? So right now it is not removing liability. I need to update that slide. Sorry, lawyers. But there is thought that if you're burning it off, it's better than just throwing it in a landfill. Granular activated carbon, minimal maintenance. You kind of, you put it in the vessels, you turn them on, you run. Not a lot of moving parts, not a lot of stuff you have to do while it's operational. And we're finding, again, this varies depending on your water quality and concentrations, but it's lasting, several months to a year in service before change out. So you're not changing it out overly frequent. Please put the parentheses around all that because depending on your water quality. Single pass ion exchange. This is unique, especially in Southern California. It seems to be doing really well with our water. It has a lower empty bed contact time. To put in perspective, carbon to treat the same amount of water requires a 10-minute empty bed contact time. Single pass ion exchange resin can do the same treatment in 2 minutes. So what that means is you can flow a lot more water through the same amount of media and get removal. That means less equipment, smaller footprint. I've noticed that that's been a big positive. So let's say the cost of treatment between carbon and ion exchange is similar, but you have to buy, only a third of the equipment to do ion exchange, and you're limited on space. Your property can only hold so much. It's pushing people to pick ion exchange for that reason. If they don't have the land, they don't have the real estate, and they don't want to, buy 3 times as many systems to accommodate the same flow. So that is a big advantage of ion exchange. It doesn't require any chemicals or anything other than the only pre-treatment is those pre-filters, but it operates similar to granular activated carbon. You put it in, you turn it on, you run it till you get breakthrough, and then you change it out. Spent resin can be handled either via incineration or landfill. Again, I did not update this. I need to correct it for the lawyers. Right now, you're not getting a certificate of destruction for the PFAS, but again, the thought that is incineration destroys the compounds. So you're not just, if you choose incineration versus landfill, you're not just, moving your contaminant and putting it somewhere else. One note here, I have the term here, single pass ion exchange. What that means is it's a one-time use, a single use, and then you remove it. It is not regenerable. I get asked that a lot. Can you regenerate it? Yes, sort of. The product that it takes to regenerate is not safe for drinking water, and ironically requires firefighting foam on site to extinguish it. It's a big risk. So at this time, there is no regenerable ion exchange for PFAS treatment, not one that is feasible. and we are just doing single pass or single use. So when it's spent, you remove it and start fresh. Membranes or RO, reverse osmosis, or ultrafiltration is another option. This has been really good because it basically removes everything. So like all those small chains, all the PFAS, you know, we talked about those 5,000. It basically is extremely effective, uses very tight filtration membranes to filter out all the contaminants. The challenge is you get a waste stream that can be around 20 to 25%. So now you have this concentrated waste stream that you got to figure out what to do with. And do you need to treat that before you send it to the sewer? Will sanitation district allow you to handle it? And the pumping costs and energy costs and capital costs are very high. So right now, I have yet to have somebody choose that over the other two due to those costs, barriers, and the waste stream. Keep in mind too, if you have this waste stream, if you're pumping 1,000 GPM, you might be only sending 7,500 to 88,000 GPM to your customers, right? So some can't overcome that loss in production. For that reason, I really focus on granular activated carbon and ion exchange as solutions at this time for PFAS. Stephanie, do we have any questions at this point?
Yeah, we have a couple. Where to go? What is the range of cost for a pilot scale test?
Okay, so the one that Orange County did that is the most elaborate one I've ever seen, cost in the hundreds of thousands. A normal, you know, maybe 4 to 5 columns testing a couple different things. The skid itself is minimal, a couple $1,000, and then it's the analytical. So if each test runs, I think, around $250 to $300. So depending on your sampling frequency, you'd have to plan on sampling for about 6 months to a year. It could run tens of thousands. Again, it kind of, the variable is how often are you sampling and how many different products do you want to test and compare. But the actual apparatus is a couple $1,000s. That's not the expense, it's the analytical.
Okay. Doesn't the health department take all of the factors mentioned and actually pre-approve the type of media that will be acceptable for use to ensure proper PFAS removal?
Yes, they do. So in our case, Department of Public Health, or DDW, they go by several names these days. They want confirmation that the products you're using are NSF drinking water approved. 2, that they do get the removal that you are saying will, and their permit will state you're allowed to use product XYZ. For that reason, pilots and RSSCTs are being discussed. Oftentimes they'll ask for you to do a pilot or RSSCT to get approval to use certain products. That is what I'm seeing. Almost everyone's having to do some kind of pilot RSSCT to use the product they choose to use.
Okay. One more question. Was the GAC that was tested for PFAS removal virgin coconut based or bituminous coal based?
They tested both. Right now we're seeing the best results from bituminous and subbituminous coal-based carbons. Those tend to have better results for treating PFAS. The coconut has a tighter pore structure, and I think for that reason, it's just not removing as well. You do get some removal, but when you talk about life expectancy of the media, we're seeing longer expectancy with bituminous or subbituminous products.
That's all the questions we have right now.
Okay. So here's going into a little bit more detail. I kind of touched on this on the earlier slide. So resin, you only need 2 minutes of empty bed contact time. Empty bed contact time is a function of how much media, the volume of media in your vessel, and the flow rate. So for resin, you need a minimum of 2 minutes to get removal of PFAS. Carbon, you need 10 minutes. RO, you also need 10 minutes. Kind of this is repeating itself, so sorry about that. Because you can run a higher flow, so using the example of that large 12-foot system I showed earlier, using resin, you could feed, 1,600 to 2,000 GPM per system. Most people are planning around 1,600 GPM because as you go up to 2,000, the pressure drop goes up exponentially. So there's like a sweet spot around 1,600 GPM that your pressure drop is reasonable and you get great flow through a system. That same equipment treating carbon, to accommodate 10 minutes empty bed contact time, you can treat 500 or up to 550 GPM through the same equipment. So you can see you would need 3 times as much equipment to treat the same flow using carbon as resin. So when we talk about larger footprint, that's how that relates. Resin, this is like a really positive thing too. It can be used seasonally. Resin, you can turn off, mothball it, and then come back, in a couple months and turn it back on and use it. Carbon can't do that. Carbon, its greatest property is that it has this huge pore structure. Bacteria loves it. So if you're not running water through it constantly, you will get a bacteriological contamination. And oftentimes that's hard to clear up. There's caustic washes and things you can do to treat it, but it's not as easy. Resin, on the other hand, you can turn off, and when you're ready to use it again, you just do a flush sequence and you can go back into operation. So sometimes that's a big deciding factor, right? If you only have a well that's operating during the summer months and off the rest of the year, having that flexibility might be key in your decision. Then disposal is similar. Carbon goes through reactivation, which is sort of an incineration process. They put it in a kiln, heat it up, burn off the contaminants, and then reactivate it and package it for future use. Resin is full incineration. They do burn it to destroy it completely. I often get asked what happens, after you burn it, where does it go? There are thermal oxidizers and other treatment systems treating the flues off of both of these kilns and incineration facilities. So the plan is to keep treating it until it's not being further released into the environment. The bottom line is every system is a bit unique, and you have to look at the whole picture for your facility and your water to figure out what's going to be the best. We are able to do life cycle analysis, so we can compare, carbon versus resin, different carbons, different resins, and see how long each will last, and then extrapolate out, cost to treat versus capital, 20-year owning. All of those things are resources we have available to you that you can start with before ever going down the path of running pilots and spending all this money. So my best advice at this point is, if you're just looking at treatment and go, gosh, what do I do now? Have this discussion of like, hey, what are my options? Here's my water quality. Can you run some scenarios for me? There is modeling I can do. What I need to know is, what is your flow rate? What is your operational schedule? Is it running 24/7? Is it running seasonally? How do you blend your wells? Is it this one's 50%? All those things. And then as far as actual water quality, I need to know the sulfates, nitrates, chlorides, TOC, your PFAS concentrations. I want to know what else is in there competing. Do you have any VOCs you're also treating for? Do you have PCE, TCE, any of those things that we need to take into consideration? And then with that information, I can do models and show you what your options are. From there, you can decide, okay, I want to go to a pilot or RSSCT, or kind of figure out your next steps. But you do not need to jump right into buying and spending all this money on pilots right away. So don't stress about feeling you have to go that way. This is a nice little infographic showing short chains versus long chains. In the PFAS vernacular, there's people talk about long chains and short chains. This kind of shows you what that means and what that. So it's just talking about the carbon backbone. So short chain is just that. It's got fewer carbons on the backbone. Long chain has longer. There's a lot of talk and concern about these short chains, right? Like right now, we're only being regulated on PFOA and PFAS. So as the regulations build, they're probably going to tack on some other compounds that we're going to need to monitor and treat for and be regulated upon. And some of those are going to fall to the short chain. So when we're evaluating technology and the best choice for you, we'll also want to look at what short chains do you have and which media is working best for those. Right now, I'm seeing the resin doing a great job with the short chains. But short chains are also removed by carbon, so please don't be fearful if you have carbon that you're in bad luck. But this is what they're talking about. So if you hear the term short chain versus long chain, they are talking about the carbon backbone and some of this PFXA, XS, PFBS. These are some things that you'll start seeing that we're going to be monitoring and could be added to the regulation. So now I'm going to go back and talk about carbon and kind of how it works, the basics of carbon absorption, lead lag design considerations, when do you change it out? I call this like carbon 101, right? How does it work? Why does it work? And why is it effective for PFAS? So carbon in drinking water typically comes from bituminous-based or coconut shell. So I got this question earlier, what was doing better for PFAS treatment? Coconut shell is depicted on the left, has a ton of these really tight graphite layers, lots of pore space, but it's very tight. Bituminous and subbituminous doesn't have quite as much pore space, but it has bigger pores, so it can accommodate bigger compounds. In the past, you may have seen it more commonly used for surface water where you're dealing with color bodies or odor, things of bigger molecular structure. Coconut historically has been really good for chlorinated solvents, TCE, PC, because they're very small. It utilizes that extra pore space to do it. One way to look at it is that pore space is kind of like highways, and then there's streets and alleyways. Bituminous and subbituminous has a lot of highways. Big stuff can get through. And we're finding with PFAS that seems to be helping. Another little infographic that shows that idea. Transport pores, where the white space is, that's your highways. That's where everything is moving through within the carbon. It's getting to those deeper pores. And then along the platelets is where you actually get absorption. That is where your removal is happening. So the white space is your highways, and the platelets are your parking lot or your garage, right? That's where it's actually going to absorb onto the carbon. And coconut, the pore structure, the highways are a little bit smaller, and only smaller things can get through. Excuse me. What is unique about activated carbon? So carbon has incredibly high surface area per unit volume. So 1 pound contains enough surface area to cover more than 90 American football fields. It's remarkable how much pore space and that's available there. It's inexpensive, so great combination. Another thing that makes it good for our use in drinking water is that it has a poor affinity for water and a strong affinity for organics. And then this pore structure that we just talked about before makes it really suitable process for absorption. So basically, carbon is our friend. It's inexpensive, has amazing capacity, and can treat lots of things. Now, I get asked this a lot. What is the difference between adsorption and adsorption? So adsorption is what is happening on carbon. It's a surface reaction with those graphite platelets. It's an attraction, right? So it's kind of like a magnet. It wants, the contaminant or PFAS wants to stick to those platelets or the graphite layers, and it sticks there. Adsorption is, it goes in and it swells. Think of like a sponge, how it expands as it absorbs. That is not what's happening in carbon. Carbon does not expand as it gets used up. Everything's just kind of sticking to internally in those little pore structures along the platelets. For that reason too, certain things that have a stronger attraction will stick better. So depending what else is in your water, the background, it may prefer that over your PFAS. And those are the types of things we look at, A, in the modeling, and B, when we're doing piloting in RSSCT, is how are those background things impacting how much PFAS is being removed. I love this page. I think it's such a great picture showing of what's going on in your vessel. In your carbon bed, when you start, your fresh carbon is this green. Everything is clean, ready to be, start seeing adsorption, and your dirty water is coming in at the top, and then you have this adsorption zone. So in this picture, there's that orange bar. That is where the actual removal or adsorption is happening. And it moves its way down the bed as the carbon gets spent. That adsorption zone is also known as the mass transfer zone, or MTZ. So again, talking about vernacular in the world of PFAS, MTZ, short chain, long chain, EBCT, hydraulic loading, these are all kind of terms that you're going to hear a lot of. So this little infographic shows how the mass transfer zone is moving through the bed. And your contaminant is working its way down, and now you get to this third one, and you start to see breakthrough. Breakthrough is also known as detection. So you start to see some of it breaking through. And then as it breaks all the way through, so that the influent equals the effluent, that dictates the length of your mass transfer zone. So this last red bar would be your vessel, the media is completely spent, and your effluent water quality should equal the influent. You're no longer getting removal. All the media has been used up. Now, the last length of the mass transfer zone is a function of your flow rate, what contaminants there are, and the size of your vessel. So, sorry, there's somebody at my door. In LGAC system, that mass transfer zone can be a couple feet within the bed, or it can be short. You also might see kind of some banding form. So some things break through soon, some compounds will break through sooner than others. In most of the PFAS applications, at least that I'm reviewing, PFOA seems to be breaking through before PFAS. So PFOA seems to be the compound that's driving changeouts. This little breakthrough is what's going to, is what you're tracking for your permit, and it's going to indicate when you need to change out. Some best practices for PFAS removal and just general also with carbon. You need, for PFAS, you need a 10-minute removal and to bed contact time. So if you go any shorter than that, you might get early breakthrough. You're also not going to get the longest life of your carbon. So we recommend 10 minutes. In the past, if you were treating other chlorinated solvents, you might have been treating more around 5 minutes. So if you have an existing treatment plant, you may need to add vessels to now accommodate the same flow but longer contact time. So that's something to consider. Increasing the flow rate will spread out that mass transfer zone. and it can impact your usage rates. So here's just, and then this bottom little bit is just some information about other compounds depending on what you're removing to show you the empty bed contact time needed for them. Hydraulic loadings. We want between 1 and 10 GPM. The sweet spot is 3.5 to 5 GPM per square foot. Hydraulic loading is a function of the flow divided by the cross-sectional area of your vessel. So, you know, a carbon train, a 12-foot diameter carbon train treating 500 GPM, you've got 500 divided by 113 square feet. 113 square feet is the cross-sectional area. You're at 4.42 GPM per square foot. So you're right in that sweet spot of hydraulic loading. Empty bed contact time is calculated by converting the volume of carbon or media in the bed, converting it to gallons and dividing it by the flow. So to get your 10 minutes, that's how you calculate that. Some basics of ion exchange. Actually, I'm going to pause for a minute. Stephanie, do we have any questions right now?
Yeah, we do have one question, and we might want to consider taking like a 5-minute break.
Great.
Right about now. So let's, the one question I have is, can you use GAC in a single pass resin vessel?
Yes. Yep. You may want to just confirm the nozzles, but it's easier to go from carbon into ion exchange than ion exchange into a carbon vessel. So yes, you may have a little bit higher pressure drop depending on the size of the screens at the bottom. But yes, it's doable.
Okay, great. All right, I don't know if you want, if this is a good time, but if we want to take a 5-minute break to stretch your legs, grab some water, and let's be back here. You guys alert.
Helps me too.
Yeah. Okay, are we ready? I do have a question if you want to start off with a question first before we get going. Similar to PCE and TCE removal, would a lead lag configuration of vessels provide improved protection potential MCL violation since the lead vessel is monitored for breakthrough and the lag vessel ensures compliance in effluent?
You might be my favorite student, and perfect segue into what we're about to discuss. Yes, and I'm going to leave it up there because you actually gave me the perfect lead into about 4 slides from now. So well done.
I'm flattered I'm your favorite student. Thanks, Matt. All right, that's all the questions we have right now.
Okay. So yeah, I'm going to get into lead lag, about what it is, why we consider it, and all those good things. But first, I'm going to dive a little bit more into ion exchange, the basics of how it works. So we talked about carbon and how it's a surface reaction, and it's kind of this attraction or force that's keeping it sticking to the platelets of the carbon. Ion exchange is a little bit different. Then we're going to talk about lead lag configuration and why it's wonderful and helps everybody. And then we're going to talk about change outs and what they look like. So Evoqua's most commonly used ion exchange resin for PFAS treatment is called PSR2+. It has a really high capacity and attraction for PFAS. This little arrow chart to the right there shows how it's selective. So selective means it wants that compound. So it is most selective for PFAS, PFOA, than perchlorate, but it also likes nitrate, sulfate, and chloride. So if you remember from 10 minutes ago, that when I want to run those models, this is the type of stuff I want to know. I want to know what's in the background because I know it's competing for space on that resin. PSR2+ really has a high affinity for PFOA and PFAS, so it prefers that over the others, but if you have a lot of the other compounds there, it's going to have an impact. I like to use this analogy. Sometimes I get a laugh. I can't see your laugh right now, so please indulge me. PFAS and PFOA, we're looking at parts per trillion. It is such a small concentration, whereas nitrates and chlorides and these other things, they might be in parts per million or parts per billion, right? It's factorials bigger, higher concentrations. So if you picture you're like a big, strong guy, you go into a bar and you're by yourself, you could probably kick everybody's butt, right? That's PFAS. It's the strongest one in the room. This resin loves it. It's gonna, it's gonna stick like perfect. But let's say there's like 20 smaller guys and they decide to pick a fight with you, Mr. Like Muscles, you're probably gonna lose. And that's what's happening in your water chemistry. If you have these other things that aren't as selective, but you've got a lot of them competing with this parts per trillion, it's going to win some of the time. So hopefully you guys are all giggling. But that's the analogy, is if you have a lot of these other competing things in the background, it's going to impact the life of your resin. So you get extremely long throughputs. With the water I'm seeing, and I'm using Southern California as a collective, the models I've done, the pilots, you're getting about 8 to 14 months of bed life out of a single resin bed. So you're changing out, about once a year. So extremely long throughputs. This is kind of off subject, but not really. Resin 2, in the same, those 12-foot vessels, we were talking about 1600 GPM versus the same ones for carbon doing 500 to 550 GPM. Another difference is those same vessels, you'd have used different quantities of material. So resin, because of needing only 2 minutes empty bed contact time, to achieve 1600 GPM, you'd use around 425 cubic feet of resin, whereas to do the 500 to 550 GPM with carbon, you would use 700 cubic feet of resin. So there's different bed volumes depending on which product or which technology you're using. That's something to keep in mind, because another, vernacular for PFAS is bed volumes. We talk about how long something lasts based on a bed volume. Know that a bed volume of carbon is typically around 700 cubic feet. It could be 1400 cubic feet if you're dealing with one of the double height vessels. Whereas resin, you're typically in the range of, say, like 350 to 600 cubic feet, depending on how you're designing the flow of that train. So something just to keep in mind. All right. Here's just a close-up of what resin looks like. It's kind of got this amber color. Starts out a little bit more on like the clearish side, and then as it gets used up, it gets darker. But when it's shiny and new, it looks like this. It's fairly uniform particle size. Some resins are more Gaussian distribution, where they have a lot of small beads, then some big beads, and it's a little bit more of a mix. PSR2 Plus is fairly uniform. It's a much tighter distribution. So this, you can kind of see it in this picture. The reason for that is we found at this size, we're getting excellent capacity without very high pressure drops. Sometimes when you have more smaller beads, it packs a little bit tighter and can cause pressure drop increases across the bed. So this was kind of the sweet spot as we found it. One other thing I get asked is, it's a gel-based resin. What that means is the actual plastic beads that are used to make this start from a gel substrate. It is not gel in the fact that like you could squish it, and it's not squishy. They're hard, they're kind of like glass. They do not compress, so it's not like as your system's up and running for years or that it's going to compress over time. It is like glass. They're extremely hard. It's the substrate used to make the plastic beads that is a gel. So a little bit more about resin and PSR2 Plus. It is NSF 61 approved, so this is what we talked about of the drinking water standard. It has been approved in many drinking water sites in Southern California. Right now, it is the most commonly used resin for perchlorate and PFAS removal. So I'm not having any challenges getting it approved for permit. We talked about those acceptable products listed on your permit. This one they're very familiar with. Because of PFAS, I am seeing they still want to see these pilots or RSSCTs to demonstrate that with your water, it's getting similar results to your neighbor a mile down the street. I am hoping and praying that they start to let up on that and just say, hey, my next door neighbor's using this, can I too? We're not there yet. Resins can remove both shorter chain and the longer chains. So let's say this new regulation comes out and now there's one more thing you have to track. Your existing treatment system, whether it be resin or carbon, still works. What's going to change now is your breakthrough. So depending on which now of these compounds breaks through first, instead of lasting, say, 280 days, now it's going to last 270 days because now you're tracking this other thing. So a big question I get from people is like, gosh, I just spent all this stuff. As the regulations change, am I going to have to buy something new? Not necessarily. What's going to happen is you'll probably have to change out a little bit sooner. But the same equipment, same media right now is going to do the trick. Minimal maintenance is required. This little picture here is showing a bank of smaller units. This was out in a part of the country that they only operate seasonally. So during the winter months when it's freezing there, they move these into a building, and then in the warmer weather, they bring them out. For that reason, they picked these little, they're about 4-foot diameters, maybe 7 or 8 feet tall. They're on little forklift channels, and they just bring them out and they pipe them up to this valve tree. So there's options like that too. You don't have to do these big 12-foot vessels. You can do these little ones. Those little ones there, the 4-footers can handle 200 GPM each. So you can string together a couple of those. Maybe that's a solution if you need temporary treatment and you don't want to, build this massive treatment plant. You can put together several of these littler ones and just set them in place with forklifts. So this is a nice illustration of what other options you have. These ones are for ion exchange, but there are carbon vessels that are like that too. Just again, you'd only get maybe 50 GPM out of the same vessel if you're using carbon. A lot of stuff is kind of the same as we said. So what is a resin bead? A resin bead is basically a plastic bead with all these little fixed positive sites and then chloride anions that are what's exchanging. So it's physically exchanging a chloride for your PFOA or PFAS or nitrate or sulfate or all those other anions you have. So if you want to picture your little bead with all these hands, there's only so many hands, right? It can only grab so many things. And once all the hands are full and holding on to something, your bead is spent. It does reach an equilibrium, but so when you say spent, it means every hand is holding something and you're done. It can't do any more. But it is exchanging a chloride for your contaminant. So you might see a slight rise in chloride concentration in your effluent, especially just at the initial startup. Another fun thing that you'll see is if you have nitrate in your water, you might get complete removal for like the initial day or so. Some people get really excited. Don't get too excited. It will break through pretty quickly. And then it's not the magic bullet that will also remove nitrate. Here's a nice little graphic showing that chlorine exchange. So basically you're releasing a salt and capturing the PFOA. Any questions at this point?
Yes, we have one. Can the little vessels be placed in lead lag configuration as well?
Yes, yep. We also have done kind of like a large manifold so that you can accommodate a bunch of them and set them up in parallel, also in series. So like, let's say you needed to treat 1,000 GPM, you put 5 in the lead position, 5 in the lag, hook them up to this, with cam lock fittings and hoses up to this kind of central valve tree. And yes, or you could just hook up hoses from the lead to lag and keep it super simple. But yes, absolutely.
Okay, that's all the questions right now.
Okay, we've even had in some sites where it was more of an industrial with very high concentrations where we've done mid lead lag using the small ones. so that you can get even more efficient use of your media. All right, so we talked about this before. This is just a fun little graphic that shows when you have a new ion exchange bed, it's all in the chloride form. It's all fresh resin. And then as you start to flow water through it, the chlorides get bumped off and it starts absorbing nitrate, sulfate, and PFAS. Now, if you remember that selectivity chart, you kind of start to get these banding, right? The things that are more selective stay to the top, stay stuck to the resin. The things that are least selective start to slough off. So you'll see the PFAS kind of stays. Now your nitrate will start to break through, then your sulfate, and then your PFAS eventually you'll start to see breakthrough. Going back to that pretty breakthrough curve slide from before, same thing's happening here in ion exchange. It's a very similar premise as carbon, just a different media to do it. But you will see like kind of slight banding. All right, so lead lag configuration. This is now going into answering the question that was asked right after break. When do I change out the media? Do you have to change it out as soon as there's breakthrough in the lead vessel? And can I switch the vessels so that the lag becomes a lead? And what are the advantages to doing that? Let's dive in. So for those that are not familiar, lead lag configuration refers to two vessels running in series. So here we have vessel A as your lead and vessel B as your lag, and your influent goes first through vessel A, then through vessel B. Oftentimes there's a sample port at that midpoint, and that you're using to track your effluent from your lead bed. There's also usually a sample point at your effluent. You want to make sure you're non-detect there. The reason we operate like this is so that you can fully exhaust that lead bed and still have the lag bed, for more removal. It's your polish, it's your safety net, and it allows you to fully exhaust that lead bed. If you did not have that lag bed to be your safety net or to capture, you would have to change out the lead bed much sooner, maybe using that 75% port, you know, in the picture at the way beginning, it was the third port down, like closest to the bottom before hitting the effluent. You'd have to change out when you start to see detection there. And as we said, your media is going to be your biggest expense running this plant. If you can utilize every bit of it, you're going to save some money. After, let's see what the next one is. Okay, so after you fully exhausted that lead bed, you use the valve tree, change the flow, and now your lag bed, or in this case B, becomes your lead. The newest resin is always in the lag position. So when we did a change out, we took out the spent resin from vessel A, put in the new resin, switched the valves, and now B is in your lead position. Now vessel B is already partially spent. Remember, it was doing some work catching whatever broke through. So when you're starting up a new plant and you have two virgin beds, you're going to get the longest lifespan you've ever gotten. On the second change out, you'll see a shorter one because that lag bed is already partially spent. By the third time, so the second change out, back when A becomes the lead again, now you're going to see a trend of what your bed life is. So any questions here about how you run a lead lag?
I don't know if there's questions on that, but I do know that there was another question that was piggyback. I believe it's off of the question regarding the little vessels being placed in a lead lag configuration as well.
Sure.
What is the cost difference given the same flow?
Gosh, I don't know. I can follow up with you on that. I know those little vessels are relatively inexpensive. They also hold less media. So, you know, I don't know. I'd have to look at that and compare.
Okay. We have another one. What lead time in ordering?
So those little vessels are usually on hand and can be delivered. They're oftentimes used as rental. The large ones, we have rentals that can ship immediately. And then for purchase, if we're building from scratch, lead times around 22, 24 weeks. We do have some on the shelf, so it just depends. It's kind of first come, first serve. But if you're starting from scratch and want us to build for you, it's about 22-week, 24-week lead time.
Okay. Any other questions while we have a minute? Nope, that's it for right now.
Okay. One question I've gotten before is, in the lead lag, do you ever just move the media from vessel B into A instead of, changing the valves or the hoses? And no, the reason you don't want to vacuum out the media and just move it from one vessel to the other is you're messing up your mass transfer zone. So if you remember the graphic from a little bit before, your spent media is on the top, your clean is at the bottom. If you vacuum it out and kind of disrupt the bed, you're going to get early breakthrough. So the best way to switch from lead to lag is to physically change valves or move hoses if you're doing a more temporary setup.
Patricia, we did have another question come in. What about lead time for resin ordering?
In stock, can be there within a couple days. With resin, we do prepare the resin, and I'll get to that. That takes about 24 to 48 hours. So, but as far as inventory, there's plenty sitting here in Los Angeles. We can deliver immediately.
Okay, that's all for right now.
Okay. This is data, again, giving credit to Orange County. This is what the results from that pilot that I showed you pictures of earlier. They operated in lead lag to demonstrate that they got better usage of the media. This yellow line, the little dash one going vertically, that shows when they would have to change out if they were only operating with a lead bed, and then allowing them to go with the lag and go to full exhaustion of the lead gave them about 10% more bed life, somewhere in that range. So here's a nice graph just showing that if you have that extra bed that lets you go just a little bit longer, how much bed life you get out of it. And that's dollars. Changing out the media is expensive, so getting 10% more runtime is a big thing. What does a change out look like? The title here says resin. Resin and carbon change outs look very similar. They both use a slurry as a method to remove and install. You can see here a manway's open and the resin there is kind of piled up. You cannot really open up that side manway normally. It will all just flow out. But in this case, they've evacuated part of the resin, drained the water, and are inspecting to see if what the condition of the bed is. This is sometimes done, let's say one of your sample taps, you're getting a detection or you're getting weird readings. Let's say your 75% port has a higher concentration than your 25 or 50% port. That's triggering like, hey, something's up. Can you come look at this? Are we getting channeling? Did the bed move? Are we getting short circuiting? What's going on? In that case, we would drain down the vessel, open up the manway, and try to take a look in to see, is that media flat? Or is it shifted to one side? Is it coned up in the bottom? Is it hollowed out, in the middle? What's going on? Is there a crust? So that's what we do during an inspection. We tend to only do inspections, if some of the things you're monitoring are triggering, like, hey, we think there's a problem, or it's during a change out. You really don't want to open up the vessel once it's operational because you risk contamination and disrupting the bed. But this is something you can do. If you get a crust buildup or some fouling on the top of your bed, it can be dealt with. We can scrape it off, package it, dispose of it, and then you keep running. So there are ways, even if you run into a problem, to try to rescue it a little bit. You may still get slightly shorter run times than if everything was perfect, but know that not all hope is lost if we find a problem. So that's what an inspection looked like. We talked about for the carbon double height towers. This is what this picture on the right, these white vessels, that is a double height carbon tower. I'm starting to see a lot of call for those for PFAS removal because of that 10-minute empty bed contact time in the limited real estate that we have in Southern California. So this one, it's basically a dual bed. You have 1,400 cubic feet or 40,000 pounds of carbon in each one of these vessels, so they can handle about 1,000 to 1,100 GPM in that same 12-foot diameter footprint. So this is an option if you're limited on space, but still want carbon as your solution. And then these are our slurry trailers. These trailers come with 3 to 4 chambers. One, usually the middle chamber is left vacant and takes the spent media, and then the one closest to the cab and then furthest from the cab have fresh media in them. So they evacuate, they use pressure and water, and they sluice out the spent media from the bottom of these pressure vessels into that middle compartment. And then after it's completely empty, they reverse the hoses and pressurize the fresh media in the trailer, and using water and pressure, sluice it back into those previously empty vessels. So it's a pretty quick process. Usually a change out takes just like a couple hours on site, maybe half a morning, 4 hours from start to finish to change out one vessel. It is possible to operate off the lag vessel only during a change out. So if you can't afford to have that vessel down for the day or two, there is a way to operate off the lag. Just have to look at your piping and the valve tree to accommodate that. Typically during a change out though, plan on that vessel being down for a day and a half, namely due to waiting for back T results. After you do a change out, you'll want to flush, forward flush, and then take your back T and HPC samples and wait till results arrive, 24 to 48 hours later to be able to put back into distribution. But the actual change outs may be 4 hours on site. The resin goes through a preparation step before it gets delivered. So one of the questions is, what's your lead time? We need to allow time to prep the resin. So, and also the slurry trailers that are doing the work. So prior to every job, the slurry trailer, the hoses, everything that's handled goes through a food grade washout and is sterilized. As the customer, you are welcome to ask for all those tickets demonstrating that that was done. It gets done between every job. So even if we use the truck the day before to do someone else and did it that morning, it's going to get done again before we come to you. The resins go through a pre-rinse procedure. Our facility that does it isn't located in Los Angeles, so it's pretty close to most of you all. And we rinse it. And the reason we rinse it is it's plastic beads. So during the manufacturing, there's some residual chemicals and manufacturing stuff left on it. So we go through this rinse procedure to make sure once it's delivered to you, you can pretty much rinse it for a short time for your back tea and then put it online. There's no backwashing. There's no long extended thing that you need to do on site. They're pretty much ready to go. We do recommend flushing for about 30 minutes to drain on site, namely so that you can get the cleanest back tea sample, right? You want to open up all your sample taps, everything, and make sure you're getting a good sample. But as far as the resin goes, it is ready to operate as soon as it's delivered because of this pre-rinse we do. We use slurry water. Nothing is touched by humans. The vessels stay sealed. The manways are not opened unless we're asked to open them for inspection purposes. If there's confined space entry or work done inside, the vessels need to be sanitized before we refill. So for that reason, we usually leave everything sealed up and do a change out using the slurry connections. Here you can see like the hoses kind of, I think I have a better picture somewhere else, but this 4-inch line, looking at this picture though, there's that vertical 4-inch pipe going along the side of the white vessel. That is your slurry inline. That's where the fresh virgin material gets sluiced in. So it kind of drops in from the top of the vessel. There's usually a water bath at the bottom to cushion so you don't damage the resin or carbon or vessel when you're loading. The empty out comes from another one. You kind of can't see it here. Let's see if I have another better picture. Okay, so this it's at the bottom of the picture here, this horizontal 4-inch line, that is where you empty out. And the vertical one where the hose is currently connected, that's how you fill. So there's cam lock fittings there. There is a cap that we disconnect. We also disinfect all the connections prior to hooking everything up. But that's what this service piping is on the side of the vessels. When you need a change out, so you're doing your monthly, your quarterly, whatever your permit dictates, you're monitoring, and you hit that trigger point. Usually permits will say like, hey, get your confirmation sample, and then you have 30 days to change out. So with PFAS testing, the results can take about 10 days to 2 weeks to get. So by the time you're getting that confirmation test, you may only have a couple more weeks left before your permit dictates, hey, you need to change out. Not a problem. It's nice to be in touch so that we're communicating if you're starting to see breakthrough, you know, like, hey, we hit 2, we hit 3, and your change outs when you hit 5 or 6. So at least we're trending it and we're aware of like, hey, this is coming up in a month or 2 or whatever it might be. But when you hit that trigger, you just call up and you say, hey, I'm hitting the trigger. Can I get on your schedule for the next week or 2? We get you on the schedule and then provide this procedure. Like I said, it's about 4 hours on site to change out a single vessel. If we're doing 2 in one day, let's say you have 2 trains and the 2 lead vessels are probably gonna need changing out at similar times. It's maybe a 6 to 8 hour day on site to do 2 at once. We can do 2 a day. Doing more than that just gets tricky with time and the resin prep and everything. So if you have a bigger system than that, you might want to scatter it over a couple days or do 2 one week, 2 the next week. Kind of think about that operationally though, what makes the most sense for you. Again, knowing that you might not be able to use that system to pump while you're changing out. Things just to consider when you're planning change outs is how am I going to operate when this one's down? Am I going to use the lag? Am I going to turn it off completely, etc. After the fill, we do flush to drain. This is a consideration you need to think about in your plumbing. How are you going to flush to drain? There's oftentimes, you know, the influent treated line, the effluent to distribution. Do you have a way to flush to drain during change outs? That is something that needs to be considered. You'll also flush daily once the change out, because if you're not able to put it online right away, let's say you're waiting for results, or you just don't need that well, you still want to flush daily for about 30 minutes just to keep bio from growing. That's good for both carbon and resin. So let's see, after change out, we always put the fresh resin into the lag position, change over all the valves so that now the previous lag is in the lead and the freshest resin or carbon becomes the polish or lag position. And then we ship off the spent media for either reactivation or incineration or landfill. Disposal options are your choice as the customer. You tell us, well, we can provide options for you and you tell us what you like. But those are pretty much your options, landfill, incineration, or reactivation. The vessel fill, kind of already talked about this a little bit. If you can keep it in continuous flow to drain, that's great. If you can only flush 30 minutes a day, that's also good. In cooler weather, you could probably go every other day. But you know, August through October around here, you probably want to flush daily and ideally at the hottest time of day. So like 1 p.m. to really get the most bang for your buck. That will help keep all the bugs from growing. Some considerations during a change out. So carbon, after you sluice in the fresh carbon, you flood the vessel and you allow it to soak overnight. The following morning, you have to backwash the carbon. The reason we backwash carbon is to remove fines and to stratify the bed. It gives you the best performance, the best or least pressure drop across the bed, and just sets you up for success right off the bat. Again, we talk about forward flushing following the backwash, but backwash is required the next day. The reason we allow soaking overnight is to remove any air bubbles that may have, that are in the fresh resin. I'm sorry, carbon. Carbon has all these pores, right? You got to give the water time to work its way through all of them and to allow that air to dissipate out. That overnight soak is what does that. If you rush that step, you may not get as good startup of your carbon. Resin. Now resin, repeat after me. I am never ever going to backwash resin. Everybody say it. I am never ever going to backwash resin. This resin, you put it in, you're good to go. Don't ever backwash it. It does not need the stratification that carbon does. It doesn't need the air release. It's good to go. Backwashing it will disrupt your mass transfer zone. It can you can lose some resin during it. Just not needed. So never ever backwash. In some of the new systems that are dual use, the piping says back. It's take it out, take off that sticker. You do not need it if you're using resin. We do recommend the daily flush to prevent biogrowth, or keep it in low flow if you can to waste until your back tees or your permit allows you to go into service. Some things to consider if you're going for long-term or short-term shutdowns. If you are going to do a long-term shutdown, which means months, or a situation where the well's down and you can't do a daily flush, you want to drain the vessel and then before bringing it online, flush to waste at as high speed as you can, the highest flow rate to waste for 90 minutes up to like 3-4 hours, depending on how long the system was offline. All right, so that gets me great to like how to manage the waste, the discharge from the system. So during startup, when you're flushing to waste, I get the question, do I need to like treat that water? Do I need to capture it? What do I, if it spills on the ground, am I spilling PFAS water? No, it's treated. It can go just to your sewer. You probably don't want to send it to distribution or into your ponds because it's, it should go to drain. It should go to sewer to waste. But there's no additional treatment that needs to be done. You should plan on, for carbon with your backwash, using about 15,000 gallons per vessel to do a backwash. And then the forward flush, the daily forward flush to prevent biogrowth is 350 GPM at 30 minutes. So gosh, what does that work out to be, like 9,000, 10,000 gallons, something like that. So just be able to manage that. For that reason, sometimes people stagger the flushing depending on what the limits of their sewer permit or system. They can't flush all of them at once, so they stagger it to accommodate those limitations. Some things to monitor on a daily basis. Before I get there, are there any questions?
Yeah, we have one question. Have you ever had issues with constant high HPCs within the GAC vessels, but extremely low HPCs at the well and the filter bag housing?
Absolutely. So GAC is that perfect breeding ground. It's dark, it's wet, there's organics. It's the perfect breeding ground for bio. So oftentimes there could have been something that was seeded, like you're not seeing it at the well, you're not seeing it in the filter bags or the pre-filters, but it somehow got in. It could have gotten in for one of those and then it just thrived and exploded. So it's not uncommon for carbon to get a bio issue. That's why the daily flushing to prevent it is so key, because it happens way too easily. It did get seeded somewhere. The challenge is, even if you had low levels before, it could have been enough to be that starter. And then you had perfect conditions where it thrived. The only way to take care of it is to do a caustic wash of the carbon. A lot of times it works, sometimes it doesn't. If the issue is really bad, your only recourse is to replace the whole carbon bed and to do when the vessel is empty, to do a system disinfection before loading fresh. Does that answer the question?
Yeah, and that's all that we have right now.
Okay. We're on the home stretch, guys. Congratulations. So general operational considerations, I get asked this a lot from the operators and the guys that are actually in the field now. They got this great new shiny equipment. What do I do? What do I check? You'll need to monitor the flow and the pressure. So if you have a well site with multiple trains, you'll want to make sure that the flow rate is evenly balanced between the two trains. Are you exceeding the design flow? You know, like if we design this for be up to 1600 GPM, you don't want 1800 GPM going in there. It's not getting the contact time it needs, or it could be disrupting the bed. Also, if it's only getting 100 GPM, that's below the low flow, and you may be causing channeling or other issues. So first, you want to monitor the flow. Second is pressure. Pressure is probably your biggest thing that you're going to monitor as an operator. You want to see if the differential is changing. So a clean bed, you may see 9 to 10 PSI drop across the resin bed. But if you go by one day and you're like, gosh, vessel A yesterday was only a 9 PSI drop between influent and effluent, and today it's 15, that tells me something happened. Or it goes to 4. Uh-oh, something happened. So you want to check pressure as your first line of defense that something isn't right. And you're looking for those changes. You will see the differential pressure build up as the bed is in service. Like we said, these are going to be in service for months to year, you know. It is going to get a little compacted over time. So there's going to be some fouling, hopefully minimal. You want to look for those changes, right? Was it always 9 creeping up on 10, but today it's 15 or today it's 4? That's going to tell you, hey, something's off. Call us and we'll help you navigate and troubleshoot what to do next. You know, do we need to drain the bed and look inside and see, you know, did the bed move? Are you getting channeling? Is there a crust buildup that's impacting your flow and thus the pressure buildup? Is your valving correct? Are you bypassing the system? It's not uncommon, like it's as simple as that, as somebody turned the wrong valve and it's no longer going through the vessel, it's bypassing it. But pressure gauges and differential pressure across each vessel will give you a lot of information. You also want to monitor the differential pressure on your pre-filters to see if it's time to change out. Typically, you change out when the differential pressure goes to 10 to 15 PSI more than a clean one. As far as water quality, you'll want to monitor these 6 items. This is telling you, you know, what's in there, what's competing. Did your water quality change at all? Do we need to review, you know, if one of these constituents increased a lot, that could impact your expected bed life. So this is what you want to analyze monthly, quarterly, whatever your permit dictates. This is also the information I need to do a model for you to help you evaluate your treatment options. Also, too, it's a really good idea to look at that valve tree, go through the valve configuration. Is the water flowing the way it should? You know, is it going through the lead bed and then crossing over and going to the lag and then out? Is, you know, kind of walk through, this should be open, this should be closed. Is the water flowing the way it should? It's really good site check to get used to doing that quick eyeball check when you're walking by. There's also these little air vac valves at the top. You can see kind of looks like a U on the top of these vessels with, I think it's a 1-inch line that comes off. If that's dripping continuously or there's water flowing out of it, that's an indication that something's up. Maybe just the seat needs to be cleaned. Maybe some debris got in there, or it could be indicative of something else. The system's overpressurized or something else. So you'll want to look to see if that's dripping continuously or flowing. That's it. There's not much to monitor. Are the flows balanced between my systems? What are the pressure drops today as compared to yesterday and historically? And are all the valves in the right position? Is the air vac leaking? That's it. Things to avoid. With resin in particular, you want to avoid chlorine and any other oxidants. Chlorine will cause those plastic beads to dissolve. And like I said, protect your media at all costs. It's your most expensive part of your treatment. So avoid chlorine. If during startup, all you have is chlorinated city water, it needs to be dechlorinated. The threshold is like less than 1 ppm. Really, no chlorinated water should pass through resin. Carbon's a bit more forgiving. Resin is avoid, avoid, avoid. You also want to avoid water hammer and rapid pressure swings. We talked about the beds moving. You want to slowly introduce water so that you're not just slamming it and potentially moving the bed either to the side or keeping it. You want to do anything you can to protect the levelness of the media in your vessel. Entrained air, let us know if your well is known to have entrained air. Entrained air can interfere with ion exchange and with absorption occurring. It just kind of, it's kind of like fouling, it gets in the way of those things happening. So if you have a well that has an entrained air issue, we may need to resolve that prior to treatment with one of these medias. You also want to use your pre-filters, prevent any particulate matter, biological growth, anything at all possible. We talked about resin having these hands. If those hands all have gloves on or are covered in a blanket, they can't be grabbing PFAS. So keep your beds as clean as possible, whether it's the daily flushing to prevent biogrowth or the 5 micron pre-filtration. Another thing you want to monitor is and avoid is resin or media loss. Loss can occur with carbon most commonly during backwash. If you ramp it up too fast and you blow it out the top, you can lose some media. Resin, not too easy for it to happen. We never ever backwash. But if a screen breaks, sometimes I've seen in those cone ones that the little nozzles will come undone, the gasket will blow, and some resin will leak out. In the design, there is usually a witch's hat or something there in the piping line to catch any media so it doesn't go into distribution. So there is a safety feature in the design there, but you want to monitor that and make sure that you're not getting media loss. The most common way I see is through backwashing. That is it. Any questions?
Does anybody have any last minute questions before we wrap things up here? I don't see anybody right now. Do you want to talk about the presentation and its availability, Patricia?
Sure. So I'll send out a link through Stephanie. I think it's going to come through. You'll notify all the attendees. There'll be a link that if you want to download a PDF of the presentation, it will come through that link.
Okay. So if anybody's interested in getting a copy of this presentation, please email shua1@gmail.com, and I will make sure that you get that. I don't see any questions, so I think we're good. Patricia, I want to thank you, for your time today. And oh, wait, hold on. Oh no, we're just having people say thank you. Thank you for your time today, so and we really appreciate it, you being here with us. As we finish out this course today, we will get to work on your certificates, and they will be emailed to you hopefully by the end of next week. They will be emailed to the email address that you used to register for this course. We are getting some comments. Thank you very much. I am someone who does not know anything about treatment, only distribution, and this was very informative. Do you provide PDH hour? I'm not sure I understand that question. But
it does go towards hours. This one will count for 2 hours towards your certificate.
Yeah,